All right, let's get started. Good afternoon, everyone. I'm Jingfeng, a researcher from Recon AIP. Today, I'm going to host the TrustML Young Scientist Seminar. Before that, allow me to briefly introduce Recon AIP to our valuable guest. The full name of Recon AIP is Recon Center for Advanced Intelligence Project. AIP was founded in 2016 as a research center for the MAX AIP project. AIP Center conducts Japan's leading AI research, which is headed by Professor Sugiyama. AIP aims to enhance the AI fundamental technology and its real-world applications. We encourage the collaboration with various researchers and engineers in related fields. We would be grateful if you could visit us in our Nihonbashi office in near future. Next, let me introduce Tuan. Tuan is just graduated.
Thanks.
At TU Darmstadt. He has an interdisciplinary background in computer science from bachelor's in Vietnam. Tuan did his master thesis in electronics and computer engineering at Hanyang University, Korea. He gains a lot of research experience, mainly in computer vision, interpreting and understanding deep convolutional neural network, entropy regularization, Markov decision process, embedded system in academy and industry. During his PhD, Tuan is researching the development of principled methods that allow robots to operate in unstructured, partially observable real-world environments. In his recent work, he proposed a framework to apply partially observable Markov decision process in multi-color planning settings. His work has been accepted, published at AJCAI 2020 and SML 2021. He's now focusing on bringing his framework to apply to robot planning problems such as disentangling and Mikado tasks. Let's hugely welcome Tuan to give today's talk a unified perspective on value backup and exploration in multi-color tree search. Hi, Tuan, please get started.
Okay, so hello, welcome to my talk. I am Tuan from TU Darmstadt, AIS, and today I will present you some of my work on improving one of the very widely used planning method, Monte Carlo tree search. And I hope that from the technique I use in my research and the very widely application of Monte Carlo tree search, we can have some insight or some outlook on how can we also not only apply it in online planning tasks, but also widely like machine learning technique. So let's start with online robot planning. So as we know, online robot planning is one of the concern topic in academia. Seen in many real world robot scenario, robots have to make decisions online based on observed information from environment. So we can see here such as human-robot interaction, robot path planning, Monte Carlo planning, or robot assembly task. However, in online robot planning, there are several remaining challenges. So such as sample are expensive. We know that because sampling of real robot is expensive due to slow movement of real robot or the expensive query of real system. And the second challenge is safety, since planning have to ensure the safety of both human and robot in some tasks. For example, in autonomous car driving, the decision have to be made optimally in order to avoid car crashing. So Monte Carlo tree search is one of the chosen methods that have been successfully applied in many, not only online robot tasks, but also in some very like game task. So for example, autonomous car driving, high-level robot planning, robot path planning, and robot assembly task. And so in this research, we raise a question as what is Monte Carlo tree search and why do we need Monte Carlo tree search? So here I want to give an introduction about Monte Carlo tree search. Monte Carlo tree search is an effective method that combines Monte Carlo sampling with a tree to make decision online. A Monte Carlo tree search consists of V node, which is stand for the value function of the state, and then Q node, which stand for the value function of a state and action. Monte Carlo tree search use simulation for planning. It consists of 4 basic steps. So in the selection step, an action is selected based on the current statistical estimated value of the tree to navigate in the tree from the root node until we get to the leaf node. And in the expansion step, when we get to the leaf node, we take an action according to the current tree policy and add a new node to the tree. And in simulation step, we run a rollout from the current state to the end of an episode to estimate the value of the newly added node. Another way we can estimate the value of the newly added node is to use a prior, could be from a pre-trained neural network. And in the last step, backpropagation, when we have the collected reward, we will back up the value along the visited trajectory. So why do we use Monte Carlo tree search for online robot planning? The reason is that it have to solve the current challenging problem. So for example, samples are expensive will be moderated by the fact that Monte Carlo tree search use simulation for planning. So it help you avoid to sample from real system. And furthermore, safety will be ensured because Monte Carlo tree search guarantee to give optimal decision. However, there are current remaining challenging of Monte Carlo tree search that we need to address. For example, first is sample efficiency, where, for example, like the sampling tree is exponentially expanded. So the sample is very expensive when we build the tree. And the second challenging is exploration and exploitation. So for example, as you can see in this case, the robot tend to choose a sequence of action to get to the goal position. But a more effective and more exploration policy here should be go down and then get to the diamond position behind the wall. So this is an outline of the talk today. We will eliminate the first problem by proposing an effective value estimation method using power mean. And for the exploration and exploitation problem, we will introduce the convex regularization framework in Monte Carlo tree search, and we further introduce alpha diversion, which we provide a unified perspective on the value and the policy function for principal exploration in Monte Carlo tree search. So first, power mean. As we know that AlphaGo and AlphaZero, which PUCT, the variant of UCT algorithm, have so great success in chess and in Go game that can beat human being. However, they need millions of samples to plan for a single move, and that is very inefficiency. And so here we want to review what is UCT. UCT follow the 4 basic steps of Monte Carlo tree search method. And here we address 2 important steps, the policy selection and the value backup. As we know in the tree, we maintain 2 types of node, which is a V, the value function of a state, and the Q is Q value function of the state and action. And in the V node, so for the value backup step, we back up the value at an average over all the tri Q node, and with a weighted for each of the branch of the Q node as small NSA divided by big NS, which is visitation count. And the Q value will be back up as the average over all the tri V node with the intermediate reward RSA here. And gamma here is the discount factor. And in each of the Q and the V node, we maintain the visitation count. So whenever we visit a node, we will increase the visitation count by 1. And so for the policy selection, you choose the action in the tree to navigate, and you based on the current empirical estimated mean value of the Q node, But of course, that current estimated mean value is not the correct one. It's only at the estimation of the current one. And you always want to estimate what is the upper confidence bound for the current mean value. And we do that using this constant C with the square root of the log big NS divided by small nsa here. And this actually follow the law of large numbers. Since the more we visit the node, the better the mean value we estimate. And in the end, this upper confidence bound will go to 0, and we will only select the action which is the maximum that have the maximum Q mean value. So however, the current average mean backup operator used in UCT have problem that it underestimate the optimal value, because we always want to go to the maximum value. But if we average over all the try V Q node, then it really underestimate the optimal branch. We can try to use maximum backup operator. So instead of average over all the current Q node, we get the maximum only, but actually it's overestimate the optimal value. And we observe here that power mean will give us the value that is in the between average backup operator and max backup operator. So what is power mean? Power mean is defined by this equation. Here I write it as a V value will be the power mean of all the try Q value. And we have the weighted for the power mean, which is the small nsa divided by big NS. So the weighted of each branch Q. And P here is constant. And we observe here that power mean is an increasing function. So when you increase the P value, the power mean of the V here will be increasing. And so the smallest one will be P equal to 1, which we get to the average mean. And when P is infinity, we get to the max. So we, based on the power mean, we propose a new method, and we name our method power UCT. Power UCT is exactly the same with UCT, but it's only different in UCT that in the way we use power mean for the value backup operator. So here, instead of the mean average over the Q, we will back up V as at the power mean of the Q. P here we consider is at hyperparameter a constant. And because Q is the transition dynamic when we take the action from the V to the Q, so Q is still the average over all the V node with the average of the reward. And for the policy selection in the tree, we still use the same technique at UCT. So it will be the argmax of the current estimated mean value Q with the exploration constant. And so we provide a theoretical analysis for power UCT. We saw a very interesting result here that power UCT share asymptotic conversion rate to the optimum the same rate at UCT. So here we analyze the limit of the probability of the action chosen at the step N, which is different with the optimal action. That limit will go to 0 when the number of sample going to infinity. This is very nice property because along with that, it shows the current overestimate and underestimate problem. It still ensures us to choose the optimum. And I think choose optimum is very important. So we take a further step to analyze the bias of the expected payoff. So with the spec here is the branching factor, that is the number of action K and the depth of the 3D. We want to give an overview of how can we derive to the theory analysis of the work. First, we make an assumption about the concentration of the power mean backup operator. So if you, for example, get P is 1, you get to the concentration of the empirical estimated mean value with the true mean value. And this assumption, from this assumption, we provide a proof for the conversion of choosing the non-optimal action at the root node, which is polynomial convert to the optimum. So this is a bit like more in the technical detail, but the proof is actually based on the induction method. So start from the leaf node. The backup should be the average, and then due to the UCB, the upper confidence bound algorithm, we always can choose the optimal action, and then we do the induction along the tree. So if we assume it correct at the depth of the tree d-1, we can derive it can correct also at the depth of the d. Here with some result about the upper confidence bound and the payoff and the concentration of the payoff. When the depth of the tree is d, we can assume it's actually the bandit that we choose the action at the current root bandit, and then go to the next level of the tree. Then we have the depth of the tree is d-1, and it's correct because we do the induction. So the assumption 1 is correct because we derive this very interesting results that we can analyze the concentration of the empirical estimated mean of estimated power mean value with the expectation of that. This is the proof for this theorem is from a very nice result of the fact that we normally in machine learning we try to use equilibrium distance, and then equilibrium distance, so we derive to the average mean, and then we have the concentration. But in this paper I cite here that Francis Dariman, he can derive the concentration for the p norm. You can refer to this paper. So when we have the p norm, which also concentrate, you have a lot of interesting results, especially in machine learning with clustering algorithm. And also I would like to show the two other very nice results with this the theorem about the bias of the expectation of the power mean with the optimum is going to 0, and also from that the concentration of any internal node in the tree is also concentrate. So yeah, so we have just tried to propose power UCT using power mean for the value backup in Monte Carlo tree search. And in experiment setup, we want to show and try to answer what is the benefit of power mean over average mean and over the max backup operator in high branching factor and in stochastic sparse reward, and also in partially observable environment. So for some of people who don't know what is partial observation, is the environment where we don't observe the state of the environment and we only observe the observation. And Monte Carlo tree search is actually one of the solver to solve that environment problem. So the first problem we want to measure is copy environment. So what is the copy environment? Copy environment is a toy task problem where the task here is that we are given an input string. So for example, here we have the input string, which is robot, and we want to copy exactly the same string to the output. So you can move the cursor, the current cursor of the mouse to the left, to the right, and you can decide which character to write to the output from a predefined character set, the alphabet set. So the number of action here will be increasing based on the size of the alphabet set. And if you write down to the output the correct character, you get the reward of 1. And if you write down the wrong character, the task will be stopped. And here we can scale the branching factor, so the number of action, which refer to the number of character in the alphabet set, to a very large number to show the effectiveness of our method in high branching factor. In the task we measure here, we do it with 2 setup, which is 144 action and 200 action. And you also can here in the task we set the size of the input string to 40 characters, so the maximum reward you can get is 40. And here we show the mean value over 1000 random seed. We compare our method with UCT, which you average mean backup operator and max backup operator. We saw that it convert to the optimum faster compared to other methods. So it really helped us for the sample efficiency problem in very high branching factor, 144 and 200 action. The second problem we want to show here is that we want to see what is the benefit of our method in high stochastic city environment. So the task here is that you are given the map. You start from the start position S, and then you want to go to the goal position G. Inside the map, there will be the red color with the H letter, which is the hole. And if you fall inside the hole, you fall the task. And if you step into the frozen cell in the map here, you kind of like third of the time move forward to the intended action, and 1/3 of the time you move to the left, and 1/3 of the time you move to the right. So it's highly stochastic city environment and sparse reward, because you only can get the reward of 1 when you get to the goal position. All other case you get 0 reward. And so we run this task compared to also UCT and to the markup operator. And so over 500 random seed here, we plot the average mean, and we show that our method with 5P is 3 outperform other method. And experiment in the POM-DP setup such as rock sample and Pocman also show the benefit of our UCT. So far, we saw our result with a fixed value of P. So in the tree, we fix the value. We try to consider P as a hyperparameter, fix the constant, and try to measure the performance. But a question have been raised at, so what if we change the value of P? So in each node, if we use different value of P, then what happened? So to do that, we provide an analysis in the rock sample 11 problem. We we plot here the result with the 65K sample, and we change the value of P from 10, 100, 150, and then so on to 500. And we plot the discount reward. And then we see that from P is 10, and then when P increase to 100, the performance increase. But then if P is decreasing, after that, the performance decrease. So actually, for a certain number of sample, you can always find a different value of P. So the best P value that you can get the highest performance. And here the performance, we saw it concavity with respect to the P. And I think we've been open many like questions that for the future work for the P adaptation. So to conclude, we propose to use power mean as the value backup operator to replace for the average mean in UCT, and we call our method power UCT. We show that power UCT enjoy the same asymptotic conversion rate at UCT, and we show that power UCT alleviate the sample efficiency problem in both fully observable and partially observable environment. And we are looking forward for the P adaptation of the power mean. So in the next section of the talk, I would like to try to solve the second problem, which is exploration and exploitation in using the convex regularization framework. So exploration and exploitation. So as we know that maximum entropy regularization has been studied in Monte Carlo research already, then a question had been raised that how about solid entropy and how about relative entropy regularization? How can that help for the exploration and exploitation? And in reinforcement learning context, there are work that is REP, and there are TRPO and FAC and so on, which already employ different kind of entropy-based regularization to have for exploration in reinforcement learning context. Boris and then later on Matthew Gibbs study the Nezen-Reffen transform and then connect all the current method in a framework, a single framework. So in this research, we want to take advantages of the Nezen-Reffen transform to provide the first conversion proof, regress bound, and error analysis for the convex regularization in Monte Carlo research. So what is the Nezen-Reffen transform? here is the definition. You can see here we have the original Bellman operator T of pi s qs, and we will regularize it using a strongly convex regularizer omega of the policy pi s. Here tau is a temperature, and the solution for this is a Laplace transform, which we derive the regular value function omega star of qs. And so the solution of this objective function, we will get to the policy that is the regular policy function, and the derivative of the regular value function will be the regular policy function. So we, based on this observation, we use the regular policy and the regular value function at the policy and the value backup operator in Monte Carlo t-shirt, and we propose a method called extended empirical exponential with E3W. So what is E3W? E3W follow the 4 basic steps of Monte Carlo t-shirt, but it of course different in the way of the policy selection step and the value backup step. In the policy selection step, we use stochastic policy instead of deterministic policy as power UCT. So here we kind of apply for some epsilon probability to sample from a uniform policy for like kind of improve the exploration. And then for most of the time, we will sample from the regular policy. And when the number of visitation increase, the probability of sampling from the uniform policy will be going to 0. And then in the end, we only sample from the regular policy. And for the value backup, we use the regular value function to back up the value. So in this work, we narrow our study to entropy based only, and we derive 3 different methods: MAN, which is maximum entropy; RAN, which is relative entropy; and TAN, which is solid entropy. And so here we want to show the entropy regularizer and backup operator of different entropy-based method, and we want to show the behavior of different entropy-based. And if we know that for the Saloon entropy, we have the softmax form for the Q value, so it assigns a non-zero probability for all the action. And the regular value function will be the log sum exp of the Q value vector. For the KL, for the Kuhnbeck-Leiberg relative entropy, we also derive the softmax form of the Q value vector, but now it will be weighted by a prior policy, because it's a KL of the prior policy with the current policy. And the regular value also the log sum exp of the Q value vector weighted by the prior policy. And solid entropy, we have different form. For solid entropy, we have the Sparmax form of the Q value vector. So now there are some action with very small value will be assigned to 0 probability, and we will assign higher probability for some other higher Q value. So it helps us like to more going more sampling into more the optimal Q value branch. And for the form of the regular value, it now not log sum exp, but the quadratic form for the Q value vector. So so that is our method, and then we provide here the theoretical analysis of the conversion rate of the choosing optimal action at the root node, and we provide here the probability of the difference between the regular value function and the optimal regular value function. So the regular value function is the current estimated regular value function, and the optimal one is the truly optimal of the regular value function. And we observe that the difference between them will be exponentially decay to 0 when the number of sample increasing to infinity. From that result, we further provide the proof for the probability of choosing non-optimal action at the root node, and we saw that it's also exponentially converged. So it actually improved over the polynomial conversion of power UCT method. And so here we want to go a bit further why it exponentially converge. very briefly sketch of how can we derive to the result with a lot of detail is not so here. But so the first one is we derive it by at the leaf node, because we derive by induction. At the leaf node, when you can estimate based on, okay, you average over all the result you collect along the sampling from the environment, or you can get it from the prior neural network. You average over that, you will get this result that the probability of the infinity norm of the mean of the current mean estimated leaf node with respect to the true mean value of the leaf node will decay to 0 based on this observation. And the v value will be also satisfy this property because of the contraction property of the regularized Lysander transform of the value function. Because you can see here that the mean value of the leaf R will convert to the true mean value with the P with an infinity norm. So the V value of the root node also. That is for the depth of the tree is D1. Okay, so let's continue, and then let's assume that by induction it correct the depth of the tree D minus 1. Then we can also, based on the contraction property of our framework, derive the property of the difference between the estimated V value with the optimum with the optimum regularized value at the depth of the tree, which is D. And then by induction, it's so it's like exponentially converge. A lot of detail have been like not showing here, but that is how we derive to the theory analysis. So there are two other criteria perspective that determine the effectiveness of an MCTS algorithm, which is a regress bound and the regularized value error function. So what is the regress bound? The regress bound is the cumulative loss of choosing non-optimal action at the root node. So how regress we are when we have a policy at the root node to choose non-optimal branch. And then because we regularize our value function, then there will be an error which is different between the current estimated value of the root node with the optimal value. And we show the regress bound of our framework here. D omega star is a Bregman distance, big O small n divided by log n, and then omega tau is a temperature, and omega is the strongly convex function. We narrow our study to different entropy base, and we saw that actually when the number of actions going to very large, solid entropy will enjoy smaller error compared to other entropy base. K here is because solid entropy will make the policy more sparse. It will assign 0 probability for some action and non-zero probability for some other action. So the absolute value of A is the number of action, where the absolute value of K is the number of action in solid entropy algorithm. And we also derive the error analysis for our framework with any omega strongly convex function, and also narrow our study to entropy base, and so that solid entropy enjoys smaller error. Here per C is actually decay to 0 is actually equal to the square of constant C hat with the with this. So we derive the regress bound and analysis of our framework, and then we show solid entropy enjoys small error when the branching factor, when the number of action is high. And in experiment, we want to complement our theoretical analysis in synthetic tree and in further in Atari game to show the effectiveness of entropic Bayes regularization compared to other methods. So first is synthetic tree environment. So what is synthetic tree environment? It actually consists of a tree starting from the root node with the depth D and then with the number of action K, so the number of branching factor. Here we can change the K and the D value. And when we get to the leaf node, each leaf node will be assigned Gauss distribution with the mean value and with the variance. And when you go from the root node to any intermediate leaf, internal node, you get 0 reward. And only when you get to the leaf node, you get the reward, which is value you sample from the Gauss distribution. So the objective of this task is to choose which branch, to choose which leaf node that have the highest mean value. And this task is very highly stochastic environment, because when we increase the depth to very big number, the environment will be very stochastic city. And it's also help us to measure the branching factor, because so the branching factor of the tree when you increase K value. So here we plot the heat map, which show the error of different entropy-based method compared to UCT. We show here 3 analysis with the error of the UCT, which is the value of the current estimated V value with the optimum value, and the error of omega, which is the current estimated V value with the optimum regularized value. We also show the re-rest error analysis here. We plot the intermediate results with the fixed number of sample, the same number of sample, and the darker color mean the smaller error, the lighter color mean the error is large. And we show that Sally entropy, we show the performance with different setting, with different depth of the tree D, and with different branching factor K. And we show that in most of the case, Sally entropy enjoys smaller error compared to other entropy base. And we further show our result in 22 Atari game. So we did 100 random seed and plot here the mean value. We compare to UCT and to other baseline method. We saw that solid entropy in most of the case obtain highest mean value compared to other entropy base, and especially in the game with high branching factor, for example, asteroid and phonic. So so far we introduced a theory of convex regularization in multicolor tree search based on Legend and Fanchen transform. We derive regress bound error analysis for our E3W algorithm and prove that E3W convert exponentially. Entropy-based regularization in MCTS help to trade off between exploration and exploitation. And in experiment, we show solid entropy-based regularization outperform other entropy-based regularization. So in the next, we try to connect the two work, power mean and convex regularization work by using alpha diversion, and we introduce a unified perspective of the value and the polyphyletic function for the principal exploration using alpha diversion. So alpha diversion has been extensive study in reinforcement learning context to have the trade-off between exploration and exploitation. So then we raise a question how alpha diversion have it in MCTS. So what is alpha diversion? So first, let's go over Kullback-Leiberg KL diversion. It's defined by this equation. Here is to measure the distance between the two probability distribution P and Q. And if we change the log function here by any convex, strongly convex function F, we get to the more generalized definition, which F diversion. But then if we study F function here as alpha function divided by this, we have the alpha diversion. So that is the alpha diversion definition. And so in this work, we will try to connect our UCT, which use power mean, and the convex regularization using alpha diversion. So how does that happen? So here's a connection to power mean. Let's start with a probability distribution A. Let's say you have a probability distribution A with n number of sampling point A1, A2, and AN. You always want to estimate the mean value of the distribution A. And normally you get it by the average over all the sampling point. So that can be with a weighted wi here. And that average mean value with the weighted wi is the solution of this objective function when you consider the mean square error, which the eclipse distance measure. If you solve this objective function optimization by using the mean square error f, you will derive to the mean average. That is the current empirical estimated mean value of the probability distribution A. But if you study, you scale the distance, which is not the eclipse distance, but you study alpha function distance, which we already defined before, which here is alpha function. You will solve this solution and then you derive to the power mean, which is very interesting and very nice property. Because I think in machine learning, normally people will try to solve the mean square error problem, try to get the average mean of the optimization. But how about we scale that with different distance measure? And so connection to the convex regularization framework here, if we narrow the study, if we study the convex regularization using alpha divergent alpha function regularization, if alpha is 1, you can get to the saloon entropy regularization. If alpha is 1, but you use alpha divergent, you have the relative entropy regularization, and alpha E2 is actually the solid entropy regularization. So that is the connection. And here we show how alpha divergent help to trade off between exploration and exploitation. This is because if we study alpha from 1 to infinity, when alpha is 1, and you see that you have the saloon entropy regularization, and you have the policy which is a softmax form, so that you have like non-zero probability for all the action. But then if you increase the value of alpha, the more alpha going to infinity, the more sparse the policy you are. For example, alpha E2, you have the solid entropy. We will assign some zero probability for some action and non-zero probability for some other action. And for alpha is 10, you assign more zero for some other action. And when alpha is infinity, you only care about the optimum action. So the scale of the alpha parameter will help us to trade off between exploration and exploitation. And so that is the alpha divergent in MCTS. And we also provide a regress bound for our method. With different value of alpha, we have the regress bound. And here tau is the temperature, A is the number of action, alpha is parameter, K is a branching factor, and n, small n, is the number of visitation, and so the number of sample. And it's actually scaled with the alpha. And if we take a look a bit further, we'll see that alpha going to infinity, it will be, in theory, it will be smallest value. But that is only in theory, because in practice, we will show that actually it trade off based on the current, based on the setup, based on the environment. So for the error analysis, also we derive the error analysis for alpha divergent in MCTS. And we also show here with alpha is infinity, it get to small lead value. But of course, it in theory. And here is the empirical result. Still, we do it in synthetic tree. We plot here with different measure with different alpha parameter from 1.5, from 1 is man, from 1.5, from 2 is solid entropy, 4, 8, and 16. And we so see that when alpha increase the value, the error is smaller, but not all the setting, because there, for example, in alpha is 16, there are still some case where is enjoy bigger error compared to alpha is 8 or alpha is 4. So it actually depends on the setup and depend on the environment that we can choose the best alpha parameter. And so far, we provide a unified perspective based on alpha divergence for Monte Carlo tree search to have balance between exploration and exploitation. We connect power UCT and E3W, so convex regularization using alpha divergence, and we derive the regress bound and error analysis of our introduced alpha divergence method in Monte Carlo tree search. And so to conclude, yeah, so far I introduced two methods, Power UCT and E3W, and then connect the two methods using alpha divergent. I would like to a bit like because I don't do machine learning, but a bit try to have some discussion like the outlook. Because, for example, as far as I can see, the maximum expected value estimation could be one of the concern topic. For example, you are given a finite number of distribution, and you always want to estimate what distribution give you the maximum mean value. So there are different ways to do that. One of the way we can think about is using power mean, because if you from the theory and from the last section I already introduced, power mean backup operator will help us to give the optimum, so the maximum expected value estimation. And as for the fixed p, and also it can help us with the p changing. So it could be interesting topic. And I don't know if somebody do online learning using RL, because for example, like you have a batch of data with x, y, x is the data and y is the label. You can try to estimate the current classifier for the current batch of data. But what if the data is not available now? It's online, for example, in some certain time you are given more data, more x and y. And if you can define the reward, which is the cost of how likely your new data for with respect to the current classifier, you can use RL, which you can you can consider that intermediate cost as the reward, and you can use Markov decision. You can formulate it like Markov decision process, and you can try to learn value function for your setup, and then you can use RL technique for online learning. As far as I know, there also one work which they try to apply RL to solve like law list graph problem. So for example, if I work for Riken, and then if Riken is in Tokyo, I will work in Tokyo. So kind of like law list graph, and then it can be solved by using RL. So for that, thanks, and I'm open for question.
Thank you very much for this great talk. There's in the chat box, there is a question by Honda-san. He said it in the rollout, some learned policies used, or a kind of random move.
Okay, so the question here from Yunya Honda is that in the rollout, some learn policy is used, or a kind of random move. Yes, so in the rollout, we can have expert policy, which is some learn policy. But of course, to be more like random increase and randomness, you also try to do random move. So we can do both. We can mix both, like some ratio for some learn policy, which is expert policy, and some ratio you can do the random move, and you can combine like 20% and 80%, or 40, 60, or 50-50, or you can only use the pre-trained neural network to estimate the value. So both can happen. Yes, thanks for the question.
I see. I think he's gone, but he got to relook the recording to check your answer. All right.
Yeah.
Thank you very much for your answering. Hi, audience. Do you have any questions? You are free to ask now. If not, if you have further question afterwards, you can email to ask his questions. Then this is the end of today's seminar. Let's thanks again for give us a very exciting talk.
Thanks for
and have a nice trip in Japan.
Thanks. It's my great pleasure to give a talk here. Thanks.
Thank you. Then bye bye. I hope to see you physically in near future.
Yeah. Yes.
Bye bye.
Bye bye.